This is Dr. Silas Conundrum of STEMpunkED. Have you ever heard of binary? It is the most basic language that underlies all of today's modern electronics, from toaster ovens to computers. You may know and use one or more programming languages already, such as Scratch or Python. But did you know that no matter what computer language you are using, underneath it all, you are just moving around the binary digits of 1 and 0 to accomplish all of the amazing things on your screen. Even this video, at its root, is the computer processing ones and zeros so quickly that they become the motion, colors, and sounds in front of you. We can see binary at work in some very crafty and fun ways, such as in weaving a paper tapestry like the one here, which you will be able to do using an activity I describe near the end of this video. If you are of a mind to try your hand at something a bit more complex, you can also use the mathematical basis of binary, called the exponential powers of 2, to convert between the decimal numbers we use every day, you'd recognize them as the digits 0 through 9, and the binary numbers 1 and 0 that computers and electronics use for all of their operations. But before we get to the activities, let's look at some of the earliest binary computing devices in history. Early machines that made the computer or electronic device you are watching this video on possible. Most of these you probably will not recognize as computers at all. Take a look at this early computing machine that is over 100 years old. Then look at this early computing machine that is over 200 years old. Do these look like computers to you? I'll bet not. Despite how they appear, these machines operate on the same principles of binary numbers as do today's computers and electronics. And just like today's computers and electronics, these largely mechanical machines use binary to make some amazingly complex results. Let's take a closer look. This machine is called the Hollerith Tabulator. It was invented as a way to manage the huge amount of data expected from the 1890 United States Census. The United States Constitution directs the U.S. government to do a complete count of all people living in the United States every 10 years. Not only do all people living in the U.S. need to be counted, certain information needs to be collected and recorded about each person, such as where they live, their expressed gender, their marital status, their age, and several other bits of information. By 1890, the United States population had grown so large that the Census Bureau projected it would take 11 years to process all of the data about those living in the U.S. That was a problem, because it would hardly be acceptable to still be working on the 1890 census for a year after the 1900 census, the next 10-year census, had to begin. The U.S. government held a contest to see who could come up with a way to shorten the time it would take to collect, record, and process all of the data from the census. The winner was this man, Herman Hollerith, a person who would start a tiny little company you might have heard of called International Business Machines, better known as IBM. Hollerith devised what at the time was considered a stunning and revolutionary way to solve the 11-year census problem, using a predecessor to the modern computer. He, of course, gave this machine a name, the Hollerith Tabulator, since it would tabulate or count or store data on the U.S. population. The revolution was based in part on this thick piece of rectangular paper called the Hollerith card. This card, along with the tabulator, was not only the key to managing the 1890 census and every census thereafter until the 1950s, but the means for programming computers for almost a full century afterwards. See the letter and number characters on this card? Those simple characters are a key part of Herman Hollerith's invention and his machine's operation. And it was the holes punched or not punched through the characters in this paper that allowed the Hollerith Tabulator to do its work. Let's take a look at how the U.S. Census was done to learn how the tabulator was used. Before 1890, and for quite a while afterward, the U.S. Census began with census workers in the field, going from building to building, house to house, to interview all of the people who lived in them to collect the census information. The answers to census questions were condensed into sheets like these, called schedules, and there were over 1 million of these sheets involved in the census. And as you can see, there was quite a lot of information on each sheet. As the schedules were completed, groups of them were sent to offices where they would be rolled onto cylinders so that the information could be viewed one line at a time by a census worker. Originally, each line of information would be rewritten into large books, which took up a lot of space and were difficult to use when looking up any single set of information. Here is where Hollerith's genius came into play. Instead of recording the information in writing, all of the data for each person would be recorded onto a Hollerith card using a hole-punch device called a pantograph. Each of those letters and numbers on the Hollerith card stood for one piece of vital census data, such as age, marital status, and more. And the holes that the census worker made or did not make on the cards allowed the tabulator to do its work. Let's look at the full process in action. First, an unpunched Hollerith card would be inserted into the pantograph. As the census worker read each person's piece of information from the schedule, the worker would use a punch guide on the pantograph to enter that person's information. Using the punch guide would create a hole in the corresponding spot on the Hollerith card. Once all of the information had been entered or punched for a person, the worker would remove the card from the pantograph. In this example of a census Hollerith card, you can see holes punched through letters and numbers corresponding to all of one person's information. A waffle press-like device seen here on the desktop of the tabulator was the part of the machine that would turn the punched and unpunched holes in the Hollerith card into usable data for the US Census. The press, seen here more clearly, consisted of a handle with top and bottom plates that could be pressed together. The punched card containing a person's information would be inserted between the plates of the press. The top plate held a series of electrically charged probes that matched the positions of each possible hole that could be made into the Hollerith card. As the press was closed, the pins would come down onto the card. If there was a hole matching an electrical probe's position, the probe would pass through that hole to an electrical contact beneath it. If there was no hole in the card in that position, then the probe on the top of the press could not make contact with the plate beneath the card. When the press was closed and the contacts were either made or not made through the card, the data was recorded for that person, and so the vital information for each person in America was recorded. To keep this video shorter, I will be using a simplified version of a question. This question is this person married? The response to this question would either be yes or no. A yes answer, of course, would mean the person is married. A no answer would mean the person is not married or single. Using the pantograph punch plate, the census worker would make the appropriate entry for the person's response to the question. The pantograph would simultaneously punch a hole in the Hollerith card in the area reserved for the response to the question. Now remember that a hole in the Hollerith card allows an electrical charge to pass into the machine, which causes the machine to count a particular answer in a particular way. This electrical charge operates the same as a light switch. Electricity either flows or it does not. It is either on or off. In the case of the question about marriage, on means yes, off means no. Here is a Hollerith census card in which holes have been punched based on a person's data. Wherever you see a punched hole, it corresponds to a yes answer to a question. Conversely, every place where there is not a punched hole corresponds to a no answer to a question. Looking at this card, you can see all of the yes responses as holes punched, and all of the no responses as holes not punched. All of this yes-no business is an example of binary. Binary meaning two. There are only two possible operations. In this case, yes or no. As far as the tabulator is concerned, yes, no are read as on or off. There either is a charge passing through a hole for a yes response, or there is not a charge passing through because there is no hole for a no response. Yes, no, on, off. Both are binary operations, just like a light bulb, which is either on or off, because electricity is either flowing to it or it is not flowing to it. So that is part of the story of how one of the world's early computers managed the US Census for about 50 years. And you may think to yourself now that Herman Hollerith was quite the smart cookie. Well, you'd be right. But if you think he came up with this idea for a Hollerith card and tabulator all by himself, you'd be wrong. Hollerith got his inspiration for his system from a weaving device created almost 100 years prior to his invention. This was the weaving device that inspired Hollerith, the Jacquard Loom. It was invented in about 1801 by Joseph Marie Jacquard. If you look closely, you can see where Hollerith got his idea for his cards. Let's see how the Jacquard loom worked. The textile industry, meaning businesses and artists who first weaved thread and then weaved cloth from that thread, was important to economies and consumers. The demand for cloth with increasingly complex and decorative weaves was more than most weavers could keep up with due to the difficulty of weaving such patterns by hand. Much like Hollerith, Jacquard was looking for a way to speed up and automate a complicated and time-consuming task. His Jacquard loom did just that. It worked by using punched cards to control the automatic weaving of complex patterns. First, an artist would sketch out a pattern. Then another artist would convert that pattern into punched card instructions that the loom could follow. The cards would then be fed through the loom to direct the weaving of the cloth. As the cards would move through the machine, metal probes would be pressed up against each card. If there was a hole punched in the card, the probe would move through it. If there was not a hole punched in the card, the probe would be blocked from moving through it. Each hole punch would be a yes operation, signaling the machine to weave a specific colored thread at a specific location in the cloth. Each unpunched hole would be a no operation, signaling the machine not to weave the colored thread. This simple system of control, yes, no, on, off, could create patterns that were both complex and beautiful. As you can see, it is basically the same form as the Hollerith card, which makes sense since it, as well as the operation of the loom itself, was Hollerith's inspiration. Simple responses that can have surprisingly complex results. These are simple binary operations. Only two choices, yes or no, on or off, that made both the Jacquard Loom and the Hollerith Tabulator early predecessors of the modern computer. So foundational with Jacquard and Hollerith cards that they were the basis for programming the first electronic computer, the Eniac. One way of programming the Eniac was through turning switches and connecting cables. Again, binary operations. A switch was either turned on or was not. A cable was either connected or it was not. In addition, the Eniac used stacks of punched cards to enter both instructions and data into the computer. Despite this simplicity, the Eniac was able to perform calculations in just a few hours that would take several days by hand. Even the Harvard Mark I, one of IBM's earliest contributions to the modern computing world, had its basic operations directly influenced by the company's founding breakthroughs. Just like the ENIAC, switches were also used to create the computer's programming instructions and data input, but in a sort of callback to the Jacquard Loom. The computer used vast reams of paper to speed up the entry of data and instructions. Here we see programmers inserting strips of hole-punched paper into rollers that would control the program's entry path into the computer. Just like the loom and tabulator that preceded it, the Mark I read instructions as binary inputs, and generated remarkable results in producing calculations far faster than humans could working by hand. As before, binary yes, no, on, off were at the heart of the machine's operations. Another way to express these binary options is through the numbers 1 and 0. 1 signaling yes or on, 0 signaling no or off. This is the electronic way of representing binary. Looking at these computing devices from 1 or 2 centuries ago, you might think that we have come so far from then in terms of our technology. Well, you'd be right, mostly. But when it comes to the fundamentals of electronics, computers, and their operations, not much has changed at all. For example, let's take a look at one of the most powerful computers in the world just a little over 60 years ago. Keep an eye out for the concepts we have been exploring so far around binary operations like yes, no, on, off, and 1, 0.
You may not realize it, but the chances are that a machine such as this one has already affected your everyday life. Complex as they look, electronic computers operate on a very simple principle. Being electronic, they have circuits that can be opened or closed, switches that can be off or on. Its understanding and its answers are limited to these two possibilities. Since this is true, how can we translate reams of data, thousands of words, complicated formulas, into the yes-no signals that the computer can understand? The answer is binary arithmetic, a system that uses only 2 digits, 1 and 0. Information to be fed into a computer is often encoded on cards, then transferred to magnetic tape for input to the computer. Holes punched in the cards represent the letters, numbers, and symbols. This data can be recorded on magnetic tape by magnetic recording heads, whose poles may be north or south, corresponding to 1 and 0. If data is fed into a computer from paper or plastic tape, groups of holes punched in the tape represent decimal and letter symbols. The control unit directs each step according to the program punched in the tape. For storage of data, on rotating discs mounted like records in a record machine. Minute spots magnetized on the drum's surface represent ones. Unmagnetized spots, zeros. Regardless of appearance, all electronic computers operate on the same basic principle, using simple language of coded signals, signified by circuits that are off or on. The productive activity of people in the future will to a large extent rest in their knowledge of computers and how to use them.
Don't let the age of this video fool you. Setting aside the leaps in miniaturization made possible by integrated circuits, which are commonly referred to as microchips, today's computers are essentially no different than these early ones, except for the speed and complexity in which they are able to manage their binary inputs, operations, and outputs. Of course, given your experience of modern computers, you may be asking yourself, why on earth were people using punched cards to program computers when a keyboard would have been obviously so much easier? Well, it might surprise you to learn that an interface that would let a keyboard and computer work together hadn't been invented yet. In fact, punched cards and punched tapes were still the primary means of interfacing with computers until the late 1970s and the early 1980s. Also, you probably think that using a keyboard to interface with a computer is a massive change in how we work with computers. Well, it is actually less different than you might guess. For example, when you press the letter A on your keyboard, the computer you are working on does not see the letter A, but rather sees a binary equivalent of A. The same is true for every other letter, number, any character on any keyboard, including the one on your phone screen. So, in reality, a keyboard, whether physical or on a screen, is just a faster, easier way to use binary without actually having to understand it. And you'll probably thank your lucky stars that your computer has a keyboard when you learn about this computer. This is the world's first home personal computer, the Altair 8800, released in 1975. This is the computer that began the home computing revolution that you take for granted as part of everyday life today. How did you program it? Well, see those switches on the middle front? Those are binary input switches. To use this computer, you would first have to build it. It came in a self-assembly kit. And then you would use the binary switches along the middle together with a few other function switches to enter a program. One set of binary instructions at a time. Can you imagine what might happen if you forgot exactly where you were while coding in a binary string? I suppose you might think, no problem, you could just look at your computer screen, like the luxurious display you see here, to figure out where you went wrong, right? Well, not exactly. You see, a way for a monitor to interface with a computer also had not been invented yet, and would not be until the early 1980s. Whether you worked on a massive mainframe like the one in the vintage video we saw earlier, or a personal computer like the Altair 8800, you only had one way of seeing your code. You would have to print it out. No matter how large that printout and the corresponding code might be, printing was your only option. To get an idea of what this meant, here is a picture of Margaret Hamilton, the software engineer who wrote the code for the Apollo guidance computer that allowed us to land on the moon. That stack of paper is a printout of the code she wrote, and wrote again, and rewrote again and again and again over 2 years. Any programmer who needed to troubleshoot code would need to print it out and go through it line by line with a special ruler to identify trouble areas. Then the programmer would have to go through the program's stack of punched cards, take out the ones with the bad code, and replace them with new punched cards with the correct code. The amazing popularity of the Altair 8800 inspired a little company to find a solution to the laborious task of entering binary code one switch at a time. You may have heard of this company. It was called Microsoft, 2 words back then. Microsoft decided to create a home version of the same punched tapes used to code mainframe computers in business. Here you see some of that original tape on display in a museum. And how, you might ask, did the Altair computer use this tape? Well, it used one of the same devices used by businesses in computing. A teletype machine. A teletype machine was used by businesses to send text messages across phone lines, as well as create, send, and receive teletype strips, which were the same as those used to code computers. But wait, you might say, there's a keyboard right there. Couldn't they use that to work directly with the computer? Well, no. These keyboards could only be used for text messages and to create punched tape programs that could then be fed into computers. Here is the punch tape reader on the teletype. Hooked up directly to the Altair, a program that would take hours to enter via the front switches could now be entered in just a few minutes. Progress is amazing, isn't it? Speaking of amazing, take a look at these folks. This is a picture of the first 11 employees of that little company called Microsoft. Now just one word. Ask yourself, if you saw a business staffed by this bunch of characters, would you have invested in it? And here, at the bottom left of the photo, is the leader himself, little Billy Gates, the genius who would one day grow up to be Bill Gates, founder and head of Microsoft. Success and time really take their toll, don't they? So now, my friends, we have a good understanding of binary operations like yes, no, on, off, and 1, 0. What's amazing is that just 2 possible responses can be combined in computers and electronics to create dazzlingly complex experiences like high-res photographs, videos, web browsing, and games. So the next time you're looking at your phone, or watching TV, or using your laptop, or setting the temperature in your house, or preparing a yummy meal, or just making your morning toast, remember that underneath it all, it's just a complex operation of binary code. Now, if you are still having a hard time seeing how it could be true that something as simple as binary code could be behind something as complex as all of your favorite photos, videos, and devices, try these mind blowers on for size. Every book, magazine, or web page you will ever read in English, every thought you will ever have or try to communicate in English, will be made up of just 26 letters and 9 digits. And if that's not enough of a mind blower, DNA, the genetic code that determines the form and operation of every living thing on Earth, from microorganisms to giant whales, is itself made up of just 4 chemicals that are combined over and over in different arrangements and orders to create all life as we know it. Given that everything you and all life on Earth are made of is based on quaternary code, 4 different possibilities, then it isn't so far-fetched to think of the video you are experiencing now as being made of binary code, 2 different possibilities, 1 and 0. Now, I love computers and use them all of the time, but more than computers, I love old analog mechanical devices that perform the same operations as computers, but in a way I can see and play around with. As a way of ramping up to the hands-on weaving and binary activities ahead, let's take a look at 2 very simple devices that demonstrate binary code and punched card programming using simple, everyday devices. You've probably seen or heard one of these before. It is a kalimba, also known as a finger drum. Watch and listen to how the musician plays the kalimba, and try to see if you can spot an example of the binary operations we have been talking about. Now that you have listened, pause the video and see if you can describe the binary operations of on-off 1-0 you see in the kalimba playing. Welcome back. If you thought that each time the player touched one of the kalimba keys to play a note, she was using an on or 1 operation, then you called it. Conversely, any key the player did not touch was an off or 0 operation because no note was played. This is a Clockwork Music Box. It is the part that makes the music that you usually hear inside some older jewelry or keepsake boxes. Just like the kalimba, this music machine is based on binary operations. Let's listen a moment while we play this old-timey, mechanical MP3 music file. Looking closely, we can see more about how this binary music machine works. The part that is rotating is called the pin drum. It is a rotating cylinder with little bumps on it called pins. Notice how the pins align to specific keys on what is called the music comb. When these pins touch a key on the comb, they strike it in the same way that the kalimba player's thumb strikes one of its keys. When struck, it plays a note. The pin locations on the drum code an on operation, meaning play the key's note. Any key without a pin aligned with it will not play a note, which means an off operation. As before, the on-off operations are the same as electronic binary operations of 1 and 0. On-off, yes, no, 1, 0. They're all the same thing. Now pay special note to where the drum's pins contact with the keys in the comb as we play this old-fashioned mechanical binary music file. Neat, huh? Now, whereas the music box we just saw was only capable of playing the same song over and over again, just like a favorite song you downloaded will only play the same way over and over again, here we have a programmable music box. You can actually code different songs for the music box to play. Any guesses as to what device we will be using to code the operations of this mechanical computer device? Well, if you guessed a Hollerith card or punched tape, you get full marks. Here is a punched tape that contains the code, the instructions for a song. Can you see the binary code on this tape? Look closely. Just as with the Jacquard Loom, the Hollerith Tabulator, and the early and modern computers we've seen, there are on-off operations that correspond to the ones and zeros. As you may have already guessed, these hole punches correspond to notes on the musical scale. When you run this program, you'll hear the composition, which is, yeah, the title pretty much gave that one away, didn't it? Happy Birthday. So now it's time to get to the hands-on binary learning activity I promised you at the beginning of this video. This base activity was made by a company called Learning Beautiful, which creates brilliant Montessori and Waldorf wood toys to teach the basic operations of computers and coding. This is a free activity that is suitable for all age ranges and can produce some very nice art pieces, which is to say pieces that are entirely unlike my artwork, which you will see soon. I have linked to this Learning Beautiful activity on my website's free resources page, and will also include it in the comments section below. Additionally, on my website are links to PDFs of my modification of their activity, which can be used to teach binary to decimal conversion. For these activities, you will need some scrap paper. The more colorful and interesting your scrap paper, the better the result of your artwork. You will also need some basic printer paper, color of your choice, to print the weaving frame template. Next, you will need a work area with scissors, ruler, and pencil. Here is an example of Learning Beautiful's loom for creating a 16 by 16 binary weave. This is the size I chose for my example, but Learning Beautiful includes templates for 4 by 4 and 8 by 8 creations that would be more doable for younger students. It is a piece of paper into which you will cut slits that you will then weave strips of paper through to create a pattern. And this is the particular weave pattern I chose for my artwork out of those provided. Working with this pattern is an example of binary coding in the same way that the Jacquard and Hollerith cards are. The only difference here is that the on or 1 codes have us weave strips on top of the loom so we can see them, and the off or 0 codes have us weave strips under the loom so they cannot be seen. Here is my binary code weaving project using the 16 by 16 loom. By the way, the size refers to how many vertical and horizontal strips there are in the weave. I have already completed most of the weave, but I left a few lines to show you how the project works and how it relates to binary. Reading the binary on-off 1-0 pattern, I should begin weaving this strip as follows, from right to left. Importantly, you should know that this is the direction you read binary numbers, from right to left, which is the opposite of how you read decimal numbers. Pause the video and try to figure out the binary instructions I followed for the first 5 strips to the left of the arrow. Use 1s for every time you see the black strip, and 0s for every time the black strip is hidden by the loom. Remember, only the first 5 strips. Okay? Pause the video. Okay, welcome back. Let's see if we can figure out the binary instructions I followed for the first 5 strips. First, let's just identify where the ones or on yes operations go. The ones signal every time you see the black strip, so they go here. Next, let's identify where the zeros or off no operations go. The zeros signal every time you do not want to see the black strip. Excellent. Now let's read this number in binary. Remember that binary is always read from right to left. The binary code for the first 5 strips is 10101. Let's do another. Try to determine the binary code in this entire line, starting from the right and moving to the left. Pause the video now and try answering. This one was pretty easy. As before, let's just identify the ones. Which weave color indicates a 1? If you said black, you nailed the yes on operation. Okay, how about zeros? Which weave color indicates zeros? If you said white, you're batting 1,000. White indicates the no off operations. All together, read this binary number. Do you remember where to start? Pause the video now. All right. In binary, this reads from lowest place value to highest, which is opposite of how you read decimal numbers. We'll learn more about that in the next section for converting binary to decimal numbers. The binary number for this entire row is 0, 1, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 1, 0. How about this for a fun fact? The number you just read in binary is the number 24,570 in decimal. Stay tuned for the next section to see how that makes sense. This is the binary pattern I used to weave my project, and you can see how it lines up here. For younger students, this 8x8 pattern that is included in the Learning Beautiful packet is probably more manageable. Using the right paper, this pattern can produce some really beautiful results. Here is the binary pattern behind this weave. It is a simple activity that can prepare younger or older students for working successfully in binary. You could even rewrite the pattern as ones and zeros. This is a variation on an AB pattern that many of you learned in or around first grade. Now this next section is for those who want to take this to the next level and learn how to convert between decimal and binary numbers. Or phrased another way, to convert between base 10 or powers of 10, which we use every day in counting and math, and base 2 or powers of 2, which computers and electronics use every day to do the same and more. This is an example of 8-bit binary. Bit stands for binary digit, which means a single digit that is either a 1 or a 0. Each place value in binary is occupied by a binary digit. Across the top of the weave are the decimal equivalent powers of 2 that correspond to binary numbers, and that allow us to convert between binary and decimal, but we'll get into that more soon. Binary was the mental experiment of the mathematician Gottfried Wilhelm Leibniz, who in my opinion should be played by a young Robert De Niro in the movie of his life. Leibniz asked himself if it was possible to represent every decimal number possible only using 2 numbers, 1 and 0. Without knowing it, Leibniz's mathematic invention actually allowed for modern computers to operate the way they do. This is an example of how binary works, both as a simple mathematical activity and as part of computer operations. Here we display binary using on and off lights, which is the same as the dots in the binary weave templates. For our first exercise, we are going to zoom in on the top binary number. The powers of 2 and their decimal equivalents are written across the top. And again, all binary operations are read from right to left, in order of increasing place value in binary, which corresponds to increasing place value in decimal. First, let's break down the powers of 2 across the top. Note that this activity is expressed in 9-bit binary, 9 binary digits, as there are 9 place values in the binary numbers we will be dealing with. In the first place value of binary, we have 2 to the 0 power, which equals 1 in decimal. In the second place value of binary, we have 2 to the first power, which equals 2 in decimal. 2 times 1 equals 2. In the third place value of binary, we have 2 to the second power, which equals 4 in decimal. 2 times 2 equals 4. In the fourth place value of binary, we have 2 to the third power, which equals 8 in decimal. 2 times 2 is 4, and 4 times 2 equals 8. In the fifth place value of binary, we have 2 to the fourth power, which equals 16 in decimal. 2 times 2 is 4, 4 times 2 is 8, and 8 times 2 equals 16. The numbers continue up to the 9th place value, or 2 to the 8th power, for our 9-bit number. Now, if you were paying attention when I introduced Leibniz, you heard me say that he wanted to come up with a way to express any decimal number, but only using two numbers, 1 and 0, or binary. But here we only see decimal equivalents for the powers of 2, 1, 2, 4, 8, 16, 32, and so on. What about the numbers in between, like 3, 5, 6, 7, and so on? Binary makes up for these missing numbers by adding existing numbers to come up with the decimal equivalents. Let's watch how a binary number becomes a decimal number. And remember that binary ones and zeros are the equivalent in computers and electronics of on and off. If a light is on, it is the same as having a 1 in a place value. If a light is off, it is the same as having a 0 in the place value. We use place values that are on or have a 1 in them to convert to decimal. The light for 2 to the 0 power is on, so we place a 1 in that place value position, and note that we will need to add the decimal number 1 to our decimal conversion. The light for 2 to the first power is off, so we place a 0 in that place value position, and note that we do not need to add a decimal number 2 to our decimal conversion. The light for 2 to the second power is also off, so we place a 0 in that place value position, and do not add the decimal number 4 to our decimal conversion. The light for 2 to the third power is on, so we place a 1 in that place value position and add the decimal number 8 to our decimal conversion. The light for 2 to the fourth power is on, so we again place a 1 in the place value position and add the decimal number 16 to our decimal conversion. The remaining power of 2 place values are off, so we can stop adding decimal numbers for our conversion. Note that even though there are zeros in the remaining positions, we still need to read those zeros in our final binary number to maintain our 9-bit number. In binary, the number we are about to convert to decimal is 1, 0, 0, 1, 1, 0, 0, 0, 0. To figure out what this binary number is in decimal, we simply add the decimal equivalents for each power of 2 binary place value that was on or had a 1 in it. Looking in the bottom right corner, you can see that those numbers in increasing value matching their place in binary are 1, 8, and 16. Now we simply add them together to get our decimal equivalent. 1 plus 8 is 9, plus 16 is 25. So the number 25 in decimal is the number 100110000 in 9-bit binary. Neat, huh? Let's try another. We'll move just a bit faster this time. Now we have the 9-bit binary number 10101010. The light for 2 to the 0 power is on, so we place a 1 in that place value position and add a decimal 1 to our conversion. The light for 2 to the 1st power is off, so we place a 0 in that place value position and do not add a decimal 2 to our conversion. The light for 2 to the 2nd power is on, so we place a 1 in that place value position and add a decimal 4 to our conversion. The light for 2 to the 3rd power is off, so we place a 0 in that place value position and do not add the decimal 8 to our conversion. The light for 2 to the 4th power is on, so we place a 1 in that place value position and add the decimal 16 to our decimal conversion. The light for 2 to the 5th power is off, so we place a 0 in that place value position and do not add the decimal 32 to our decimal conversion. And lastly, the light for 2 to the 6th power is on, so we place a 1 in that place value position and add the decimal 64 to our decimal conversion. The remainder of the place values are 0. Again, to figure out what this binary number is in decimal, we simply add the decimal equivalents for each power of 2 binary place value that was on or had a 1 in it. Looking in the bottom right corner, you can see that those numbers, in increasing value matching their place in binary, are 1, 4, 16, and 64. Now we add them together to get our decimal equivalent. 1 plus 4 is 5. 5 plus 16 is 21. 21 plus 64 equals 85. The decimal number 85 is the 9-bit binary number 10101010. So you might be wondering how binary to decimal conversions can be integrated into the weaving activity. I have made some modifications to the Learning Beautiful templates and posted them at STEMpunkED just beneath this video, so you can download them afterwards to see how it will work. I chose the 8x8 template for this exercise. It makes for a much more manageable 8-bit binary exercise. Here is how I modified the activity. There are 4 different weaving templates in the Learning Beautiful activity. For each of them, I have added the decimal equivalents to the powers of 2 binary across the top, as well as lines for entering the decimal equivalents of the binary in the patterns. In addition to weaving patterns, you can also find the decimal equivalents to binary weaves, as seen here. I have brought down the powers of 2 equivalents into the pattern and illustrated how they are added together to determine the corresponding decimal values. If it helps, you could write the binary numbers over the open and closed circles to help reinforce the idea of on, off, and 1, 0 binary. I have also modified the 8x8 loom so that students can easily see how their patterns are matching up to the powers of 2 as they weave their strips. They can even write the decimal value for each strip or row as they complete it. I have included an additional template for strips in black in case you want to duplicate the white-black color scheme of my weave to maximize contrast. Lastly, I have modified one of Learning Beautiful's blank templates so you can create activities like 1. Assign a decimal value to each row. Create a binary weave that is equivalent to the decimal value. 2. Create binary weave patterns and then calculate the decimal values for each row. 3. Assign prime or not prime numbers or some other number system. Create binary weaves based on these. We've learned a great deal about binary. Let's review. One of the earliest machines to use binary code was the Jacquard Loom in 1801, used to weave complex patterns in cloth. Jacquard's loom inspired the invention of the Hollerith Tabulator, used to process the 1890 census. which in turn provided the foundation for the operation of computers and electronics from the machines of the early 1960s to the massive supercomputers of today, not to mention your toaster oven, all brought to you by the numbers 1 and 0. I hope you have fun using Learning Beautiful's binary weaving activity, and that my modified materials for teaching binary to decimal conversions are useful. Well, that's about it for the important information in this video. For those of you who are interested, what follows is a video review of the vintage hands-on STEM toys and equipment I bring to my in-class programs related to this topic. Those programs include Home Computing 1965, Gaming and Coding Before the Microchip, and Marvelous Machines, Ingenious Marble-Based Computers. Most of what I bring are toys and tools from the 1950s and 1960s that were designed to teach children and adults about the fundamentals of binary math and Boolean logic, things that they would need to enter the new world of computer programming. Take some time to look at them to see how kids and grown-ups learned to code and game in the world of computing before the microchip was even invented. Until next time, this is Dr. Conundrum saying, stay safe, stay healthy, and stay educated.